Hi everyone, this is Adam again. So today I'm going to go over the chapter of proof by induction. So induction is something that might come up in paper one. It could be a full question, just doing a proof by induction. So I'm just going to do a little bit of kind of like proof by induction. Mainly you just learn by doing it, to be honest. Do it 2 or 3 times and hopefully it won't be too bad. I'm just going to go over a little bit of notation first before I just dive into it. And then I might do one exam paper question if I find it in the book, okay? So, first of all, summation notation is something, it looks like this. Okay, so this basically means sum. So add. So it might be something like this. So sum from r equals 1 to 10 r. So basically what this means, it wants you to add up all these r's, but the r's will range from 1 to 10. Okay, so this basically says, so first of all, you want to add up all the r's, which is 1 plus 2 plus 3 plus 9 plus 10. That's all that is. So the symbol is called sigma. It just means sum. You sum up all these r's and so on. And again, if we had something different, maybe sigma r squared, what does this from, again, r equals 1 to 10? This basically just means you add up 1 squared plus 2 squared plus 3 squared plus 9 squared plus 10 squared. That's all. Okay? So that's basically all that means. All right? So not too bad. It's just notation. So please don't get too bogged down. That's all it is. It's just a way of writing something. Okay? So the next thing that I want to do is I want to go through an example of proof by induction. So what actually is proof by induction? Basically, I'll go through I'll go through like a detailed example, but all of them will do the same thing, okay? So basically, what you're saying is, it might say prove for all n in n that the sum from r equals 1 to n of 4r is equal to 2n into n plus 1. So they're asking you to do this by proof by induction. Now, the very first thing you do, so the first step, is you prove that it's true for the smallest n. Okay, so you just prove for the smallest n. So if a question says, oh, n is an element of n, that means n can be 1, 2, 3, 4, 5. So in this case, the smallest n is when n is 1. Okay, that's the very first thing that we want to do. So I want the sum from r equals 1 to 1 of 4r has to be equal to n is 1, so it's 2 times 1 times 1 plus 1. Okay, that's equal to 4. So is the sum from r equals 1 to 1, 4r, equal to 4? Yes, it is. The sum from r equals 1 to 1 of 4r is just 4 times 1, and that's it. So you just plug in 1 here for r and you get this, and that is indeed equal to 4. So this is true. So I've shown that it's true for the smallest possible number you can plug in, which in this case is 1. Okay? So that's the very first step. The second step then is you assume it's true for n equals k. So basically I'm going to assume that the sum from r equals 1 to n of 4r is equal to, again, so I'm replacing every n that I see with a k, so sorry about that, that should have been a k, is equal to 2k into k plus 1. So basically you go back up to the original statement, which is here. Wherever you see an n, I've now replaced it with a k. So this n got replaced with this k. This k was put in place instead of this n, and this n was put in place instead of this k. Okay, so I've just replaced everything with k. So now what you're saying is you're assuming that this thing is true. All right. Now, one thing I'm going to do is I'm going to rewrite the left-hand side. I'm going to get rid of the summation thing. So what is the summation thing? So the summation thing is basically saying, if I plug in r equals 1, I get 4 times 1. Then I plug in 2. Then I plug in 3. And I keep going all the way up to k. Okay? So this is what this thing is. It's just adding up all these different things where you're plugging in different numbers here and adding them all up. And I need to, so I'm assuming that this is equal to 2k into k plus 1. So this is the thing that I'm assuming is true. So I'm taking that this is true. Okay? So assume this thing is correct. All right? Now the next thing I need to do, the third step, is to prove true for n equals k plus 1. Okay, so again, this is probably very abstract and very weird. Just bear with me for a minute, and then at the end, hopefully this will make sense. Okay, so you're proving that it's true for n equals k plus 1 using this. Very, very important. Okay, it has to be using this. So now, what is it I need to prove? I need to prove that the sum from r equals 1 to k plus 1 of 4r is equal to 2. K is now replaced with k plus 1. K plus 1 is now replaced with k plus 2. So it's k plus 1 plus 1. So k plus 2. Now, what is this thing on the left? This is equal to 4 times 2, 4 times 3, plus dot dot dot, plus 4k, and 4k plus 1. So remember, we're going up to k plus 1 this time. And therefore, we're going up to k plus 1 here. Okay? And now, using this information back up here, I can say, well, hold on, if I add up 4, 1, all the way up to k, I get this thing, which means I can just replace this with 2k, k plus 1. Okay? So I can just replace that with that. And so what am I left with? I'm left with 2k, k plus 1, plus 4 into k plus 1. Sorry. Like this. I can factor out a k plus 1. So this is going to be k plus 1 into 2k plus 4. Again, I need to show that this thing is equal to this. So I can factor out a 2. So it's going to be 2 into k plus 1 into k plus 2, which is exactly what I was asked to show. Okay? So those two things matched up. So again, you assume that it's true for n equals k. Then using this fact, you have to plug it in here somewhere, which I did straight away. And I was able to show the result. Okay? The last step is basically just to say, this is kind of, this is proven true, okay? But basically the reason it's true is because, so what have I shown? I've shown that it's true for the smallest n, which is 1. I've shown that if true for one number, then it's true for the next. So basically what I've shown is, I've said, okay, assume that it's true for n equals k. I've proven that it's true for n equals k plus 1. So what I've said is, okay, if it's true for the 10th number, it's true for the 11th. If it's true for the 27th number, it has to be true for the 28th. And now what I've done is I've shown that it's true for the first number. So it's true for the first number, but if it's true for one number, it's true for the next. That means it's also true for the second number. But hold on, it's true for the second number, which means it has to be true for the third. And the fourth. And so on and so on. Okay? So that's basically what proof by induction is. It's you show that it's true for the smallest n, you assume it's true for n equals k, then you prove that it's true for n equals k plus 1, given that it's true for n equals k, and then you say, okay, I've proven it's true for the smallest one, and I've just proven that if it's true for one number, it's true for the next, and therefore if it's true for 1, it has to be true for 2. Then if it's true for 2, it's true for 3, and then 3 and 4 and 4 and 5 and so on and so on. Okay? So that's basically your proof by induction. Okay? Alright, so another one that I would like to do is this. Okay? So it's a kind of like a division one here that I'm going to do next. So it says prove that 10 to the power of n minus 7 to the power of n is divisible by 3. For all n in n. Okay? So, very first thing, again, step 1, show that it's true for the smallest n. The smallest n we can have is n equals 1. So I need to show that 10 to the power of 1 minus 7 to the power of 1 is divisible by 3. This is 3 divided by 3, which is 1, and that's an element of z. So basically, divisible just means that you get a whole number. Okay, so remember, z is all whole numbers. So z is minus 2, minus 1, 0, 1, 2, dot, dot, dot. Okay, just for clarity there. So now, I'm assuming, for the second step, you're assuming that it's true for n equals k. So again, 10 to the power of k minus 7 to the power of k divided by 3 is equal to some L, where L is an element of z. Okay, so I'm just saying that it's divisible by 3 because I get a whole number. That's all I'm saying here. So please don't get too, bogged down by what I'm doing. Just say, okay, well, it's just divisible by 3, that's fine. And I get some L, that's a whole number. So I just get a whole number if I divide it by 3, and therefore it's divisible by 3. Third step, using this fact, I need to show that 10 to the power of k plus 1 minus 7 to the power of k plus 1 divided by 3 is equal to some, maybe m, where m is an element of z. So I need to show that m is whole. Okay? So, very first thing, I need this to look a bit more like this. So the first thing I'm going to deal with is the powers. Okay? So 10 to the power of k plus 1, that's 10 to the power of 1 multiplied by 10 to the power of k. And again, 7 to the power of 1 times 7 to the power of k. All over 3. Now, I'm going to do something that's a little bit harsh, but what I want to do is I want to bring this in somehow. Okay? Actually, okay, sorry. I'm just thinking, what's the simplest way to do this? Yeah, okay, I think the simplest way to do this is to come back up here, and I want to get rid of this 7 to the power of k. Alright? So I can go back up top and say, okay, well, I know that 10 to the power of k minus 7 to the power of k is equal to 3l by assumption. So 7 to the power of k is equal to 10 to the power of k minus 3l. Fine. Now I can plug this back up in here and say, okay, this is going to be 10 times 10 to the power of k minus 7 times this is going to be 7 times 10 to the power of k minus 7 times 3 times l, all divided by 3. Okay? This now, 10 minus 7 is just going to leave me with 3, 10 to the power of k, minus 7 times 3l, all divided by 3. Now I can cancel the 3's, and I'm just left with 10 to the power of k minus 7l. So we have that 10 to the power of k is a whole number. 7l is also a whole number. And therefore, 10 to the k minus 7l, which is equal to m, back up here, which we said was m, has to be a whole number. So hopefully that makes sense, that if I get one whole number and minus another whole number, I'm going to have to get a whole number. Okay? That mightn't be obvious at all, but if you did 10 minus 8, 15 minus 3, 27 minus 48, all these different, you could do whatever you wanted, you're always going to end up with a whole number. You're never going to end up with a 0.5 or a root 2 if you do 10 minus 7 or something like that, So that's why it's always going to be a whole number, okay? All right, now I'll do inequalities as well, because I'll do one inequality question. Now, I don't think these have come up before on the Leaving Cert, to be quite honest, but I am going to do one just because I think it's very, very difficult, okay? All right, so now, the next one that they ask me to prove is they say, okay, prove 4 to the power of n is greater than or equal to 4n plus 1 when n is greater than or equal to 2 and n is an element of n. So what they're saying is, they're saying now that n is basically 2, 3, 4, 5, all the way up. Okay? So now, first step, you prove it for the smallest n. What's the smallest n here? In this case, it's 2. So you show that this is true for n equals 2. So you say, okay, is 4 to the power of 2 greater than or equal to 4 times 2 plus 1? 16 greater than or equal to 8 plus 1, which is 9. So I get that 7 is greater than or equal to 0, which is true. Okay, so this is true for the smallest n. Perfect. The next thing I'm doing is that I'm going to assume that 4 to the power of k is greater than or equal to 4k plus 1. Okay, so I'm assuming this is true. Third step, because this is true, I need to show that 4 to the power of k plus 1 is greater than or equal to 4 to the k plus 1 plus 1, like this. Okay? Now, these inequalities are quite hard. Okay? I'm going to do a quick little example that if A is greater than or equal to B is greater than or equal to C, then this means that A is greater than or equal to C. Okay? This is how I'm going to prove this one up here, using this. So what I'm going to do is I'm going to say, okay, so I can't, so again, remember, you have to use this somewhere. So you can probably imagine that I'm going, this is what I have, which is here, and I'm just going to plug in an extra inequality in here. Okay, and that's going to be this thing up here. But basically, I want this to kind of look similar to this. Okay, so on the bottom one, I can change this. That's the same thing as 4 times 4k. Okay. And from the top one, I can say, well, hold on. So this is greater than or equal. So I want to show that this is greater than 4k plus 5. But from the top one, I can say that if I multiply both sides by 4, I get that it's greater than or equal to 16k plus 4. Okay, so again, I just multiplied this top one by 4 to get this. So this is what I want to show, and I'm assuming that this is true. So I don't know if this is true, but I know that this one's true. So I can say, okay, these two things are equal. Great. So if I can show that 16k plus 4 is greater than or equal to 4k plus 5, then I can conclude that this is also true. Okay, so again, hopefully that makes sense. But just think about it. I know this is true, so I know that A is bigger than B. If I can show that B is greater than C, then I've shown that A is greater than C. Okay, so that's the logic that I'm using here. So I get this inequality, and if I solve it, I get that 12k has to be greater than or equal to 1, which is true. Why? Because k is an element of 2, 3, 4, ... So k is the same thing as n, basically. So k can be 2, 3, 4, 5, on and on. So again, if I plug in 2, 3, 4, 5, I'm always going to be bigger than 1. Okay? All right. And then that's it. You've proved it. There's nothing else to do. Okay? All right, I think I might leave that there for today. Hopefully that's okay. But that's how proof by induction works. It's basically you sit there and you say, okay, prove it for the smallest number, then assume it's true for a certain number, show that if it's true for a certain number, it's true for the next number, and then you can say, okay, well, I proved it's true for the first. I've also shown that it's true, that if it's true for one number, then it's true for the next number. I know it's true for the first number, and therefore it has to be true for the second number. Because it's true for the second number, it has to be true for the third number. Because it's true for the third, it has to be true to the fourth, and so on and so on. Okay? So hopefully that's all okay. But yeah, I think I'll leave it there for today. Thanks very much for paying attention, and I'll see you in the next one.